And I think now we are ready to get started. Okay, fantastic. Okay, there's two screens, so I will feel quite good about blocking this one. Thank you very much, first of all, for having me, for giving me this opportunity. I am incredibly excited, butterflies in my stomach, etc., etc. I'm just very excited to be here. I'm going to be telling you about this work that I've been doing for several years with a shifting cast of students, a whole bunch of folks. And I'm going to describe this work. So it's at the point now where I think people other than those who actually built the tool can use it. I'm not sure it's actually there yet, but I'm hoping, and we're constantly pushing in that general direction. And so this entire talk is not really going to be, but I'm trying not to make it a kind of an academic talk with typing rules and so on and so forth. But instead I'll spend the bulk of my time at Emacs just showing you how one uses, how one plays with this tool. And I'll switch every now and then to give you a little bit of background about how things are working, right? So if you have, so there will be lots of, so really the way to think about this talk is, how would a user of refinement types or Liquid Haskell interact with the system? There's a lot of wheels turning underneath the hood, and if at any point you have questions about any of it, just raise your hand and say, how does this happen or how does that happen, and I'm happy to jump in there, right? But this is a highly edited talk with a focus largely towards what a user of this tool is going to see. Okay, good. End of preamble. Let me just give you a quick overview. So I have a long session, which I'm extra grateful for. I hope no one will fall asleep, least of all myself. And I've split it into three parts. Okay, so the first part, I'm just going to explain what the hell are refinement types. So for those people who know what dependent types are, this will be quite, you'll be able to figure this out. The second part, I'll give you, so the first part will have lots of really small examples, really small sort of quote-unquote toy examples. This one, I'll show you some slightly larger examples. I should have put quotations around the case or around the studies. But these will be slightly larger examples. And then I'll talk a little bit about how Haskell, so everything I described in the first two, really applies to pretty much any statically typed functional language. In part three, I'll talk about how Haskell sort of throws a bit of a, what is the word I want? A wrench into the works, and how we solve that particular problem. And if we have time, I really don't know how long those first three parts are going to take. If we have time, I will talk about some quote-unquote advanced material, which is not really that advanced. A technique we call abstract refinements, which I think is really, really cool. I get very excited about it. But anyway, this is if we have time. So let's just jump right in, and let me give you some general motivation. So a lot of you, this will be entirely familiar to you. There's this whole slogan, right? Well-typed programs don't go wrong. This is true only if you interpret go wrong in a very precise and technical sense. And all of us know that they most certainly do go wrong in various ways. So here's the kind of hello world example of well-typed programs going wrong. Here's an average function. I add up the elements in the list x's. I divide by the length of x's. So here x is a list. If I compute the average of the list 1, 2, and 3, I get back what is the average 2, right? But God help me if I pass in an empty list, because then, of course, I get to divide by 0 because the length over there is 0, right? And these are pretty nasty. You won't know what to do with them, so on and so forth. Here's another one. I find it always amusing when people say there are no null dereferences in functional languages. I mean, technically, yes, there are no null dereferences. But the equivalent, if you wish, of null dereferences are things like this, when you look up a map for keys that are not there. And now, yes, I know about the whole maybe an option thing. But the equivalent then is when I want the value inside the maybe and it's not there. I have a nothing when I really wanted something, right? So here we go. Here's a map. I have two languages inside it, Haskell and Pyret. And if I look up Haskell, life is great. But if I try and look up a third language, Racket, again, I get one of these pesky exceptions, right? Here's another example. So, this is a talk about Haskell, and I have segmentation fault up on the screen. What gives? Well, you can try this at home, or right here, in fact. You can boot up data vector, and if I just create a little vector, let v is equal to from list, and I make a little vector with 2 elements. If I look up that vector at the index 0, then that's great, I get back Haskell. But if I try and look it up at index 3, then there you go, okay? And this is actually a pretty happy thing to happen. Yeah. Okay, it's good if you get a segmentation fault. Life is not always so kind. Here is data text unsafe, And I might pack up some string. Let T is I create a string, right, with whatever 7 elements in it. And then I want to take the first 5 things from the string, and I get the first 5 things. But if I try to take the first 50 things or the first 20 things, it will happily jog along and give me the next whatever, 14 things after the string ends, right? And who knows what was over there. So these are various ways in which perfectly well-typed programs, everything was well-typed in the in the usual sense, have gone wrong, right? And how can we extend Haskell's type system to prevent this larger class of errors? That's the problem that I care about. And really, you can start with this prevent a wider class of errors, but more broadly speaking, to enforce more program-specific properties. That's what I'd like. Okay, and I just want to paint with a very broad brush the landscape of different technologies that are out there. So this graph is not to scale, right? I don't even know what the units would be. There's an x-axis and a y-axis. The 2 dimensions I'm worried about are how automatic is the tool and how expressive, so how sophisticated are the kinds of things you can say with it. And I think there are 2 ends in this. At the one end, I'm just going to say ML, by which I mean Hindley-Milner type system, right? Or just a really nice static type system. It's very, very automatic, but it's not terribly expressive. It's very restricted in the kinds of things you can say. At the other end, I'm just going to say cock, and by which I mean, you can insert your favorite fully dependently typed system over there, right? Super expressive. You can essentially encode any arbitrary mathematical fact, but it's not extremely automatic. You have to do a lot of work to help the system check that, prove whatever thing you want proved. Here are some other technologies. The one I'm particularly interested in is a line of work that really dates to the 70s called the extended static checker, which started off in the 70s as what was it called then? I think the Stanford Pascal verifier, right? And a lot of the technology that we're using actually, started in the late 70s and is embodied in the ESC system. So if you know what this is great. If you don't worry about it. It's quite expressive. It's a little, it lets you say a lot more things than ML. It's a lot more automatic than, say, something like Coq, because you just write pre and post conditions and loop invariants. But still, it's actually quite limited. It doesn't let you say interesting things about, for example, lists or trees or hash tables or fancy data structures or higher order functions or parametric polymorphism. And so really, the limit would be something over there, but we're trying to just find some sweet spot somewhere around the question mark. Wow, that's a lot of startup. So let's just jump right in, and let me show you what a refinement type is. Okay, I think this will work if I click this link. Here we go. Okay, so what is a refinement type? Here's in a nutshell, a refinement type is simply, you start with a Haskell type and you slap on a little predicate. So here's the simplest refinement type I can think of. I'm just going to, so everything in Liquid Haskell, all the information that is conveyed to Liquid Haskell goes inside these funny comments. Okay? So they do not affect the runtime. They're literally just comments, right? They literally don't affect the runtime in any way. So I'm going to define a type, and by define a type, think of it literally as a type alias. There's a Haskell-style type alias. I just don't want to have to write all this again and again. So I'm going to define a type called 0, which is values that are integers such that some predicate is true. And in this case, the predicate that's true is just value equals 0, right? So this type describes exactly one value, the integer 0. Okay? And I can come up with this extremely profound statement that the variable 0, which is equal to the value 0, has the type equal to 0. Okay? So far, so good. So this is the sort of the simplest possible refinement type. This is kind of boring. Let's look at a slightly more interesting example. Question? Was there a question? Sorry.
Is it really equal, not equal, equal?
Oh hell! Was there a single equal there? We actually allow you to write both things. So here we go. People always get thrown off by this. So here we go. Did I not define a type 0? So here we go. So here I'm in Emacs now, right? And you could do it both ways. So here are some slightly more interesting types. Type 0, I hope I didn't redefine it. Value integer such that value equals 0, right? It'll parse both, it's the same thing. And what did I say earlier? 0 is an int and 0 equals 0. Okay? Oh, this is nothing. I'm actually told it that I wanted to have the type 0. So the way I would do that is I would say 0 has the type capital 0. Okay? So that's our very first thing. Now notice that if I make this 0 be a 10, then it's not going to be very happy about it, because 10 certainly does not have the type 0. Okay? So there we go. So this is the kind of most boring refinement type, that should give you a very simple idea. So here are some slightly more interesting refinement types. And these are all refinements of integer, right? So nat is simply an integer such that values are greater than 0, greater than or equal to. I always drop the or equal to. Pos is integers such that the value is strictly greater than 0. What is this last fellow? Oh, non-zero, values that are not equal to 0. Okay? Now one thing I want to emphasize is, let us consider, if you wish, 11. Okay, so let me write 11, and here is 11, which is equal to, of course, 11. 11 has all of these types, right? So if I say 11, I can give it the type nat, naturally, right? It is a nat. It also has the type pos, right? And it also has the type, what was the last one, non-zero. Okay? So in fact, what's going on here? How is it that it has all these types? What we'll see in a second is that underneath the hood, the basic type system uses a form of subtyping. So really, what the type of 11 is, oh, now it says non-zero because that's the signature that I gave it. Let's just blow this out. Okay, so if I remove that comment, now what it's going to tell me is that 11, come on, buddy. Oh, that's useless. Oh, never mind. Ah, sorry. Was there a question?
The type annotation entry, would that mean you could have?
Oh, I know what it is. It's a kind of, it's, okay, allow me to do this. I'm going to say 11 is equal to x where x is equal to 11. That's a really weird thing to do. But I do it just in order to show you what the type of x is. And really, the type of x is value equals 11. Right? And all these other things are super types of value equals 11. And I'll explain in a second when I get to the theory part of the show what that means.
I have a quick question.
Yeah.
What happens in the definition of 0 if you change the Haskell type annotation to double?
Oh, what happens? Sorry, this glass is maybe not best placed on an inclined. So if I go here and I change this to double?
No, the 0 : : a little higher up. Not currently showing on the
screen.
screen.
Right, okay, sorry. So
0.
if I change this to a double,
yes.
What's going to happen? Well, why don't I just show you what's going to happen instead of, So if I do this, you will get an error over here, and it's instructive to see what that error is. But unfortunately, I haven't figured out how to make these fonts larger, so I will have to just read it out to you. Specified type does not refine Haskell type for refinements.0. In particular, oh, lost you, Emacs. Oh, you know what? There's a way to get this. Yes, I know how to do this. If I just, there's some fly check trick. Why? Hang on, let's just move the cursor there and maybe it'll pop up. Oh, anyway, long story short, what it's telling you is that Haskell thinks the type is double, while you are claiming the type is an int.
Okay.
And so the type you are claiming has to be a refinement of the Haskell type.
Right.
Okay, so if there's any mismatch there, not allowed. Yeah.
What language are you writing the predicates in?
Oh, excellent. I will get to all of this in just a second. But you know what? Maybe I should just get to it right now. Let's just pop right over here, and I will explain exactly all these things. Okay? Funny you should ask. So here is, let me just describe the language that I'm using for these predicates. Okay, and this is, okay, I confess this was a slide taken from a talk given to an academic audience. So this is a kind of it's a kind of technical point, but the logic that I'm going to use in my refinements is a decidable logic. And this is something that is, what shall I say, it's a sort of religious fact that's near and dear to me. It's very important to me that this logic be very, very decidable. And it's sort of stratified into expressions and predicates, partly because I'm lame. Really, there's just one kind of expression language. And let me show you what it is, okay? So for those of you who know what this means, great. For those of you who don't worry. It's the logic of quantifier-free function, expressions of formulas of uninterpreted functions and linear arithmetic. What does that mean? This is what it means, okay? So expressions are just variables x, y, and z, or numeric constants, integer constants, 0, 1, 2, etc., right, 3, 4, 5, 6. You can add two expressions, you can subtract expressions, you can take an expression and multiply by a constant, where this is one of the constants, okay? So this is all sort of linear, essentially linear arithmetic. And this is where I'm going to pack a whole bunch of stuff. Okay, this is the big rug under which a whole bunch of stuff gets swept. It's called an uninterpreted function. Okay, so f applied to E1 through En. And I will explain what an uninterpreted function is in the fullness of time. Okay? So those are basic expressions, and then we build up, quantifier-free formulas over those. So you can have an atom, which is just an expression. You can compare, equalities, disequalities, and or not. Okay, so no for alls, no exists. It's just that's it. Okay, and I want to emphasize that any formulas over this logic that I've described, you can decide very, very efficient. Well, not very, very efficient. You can decide with an SMT solver. Right? The decision procedures for this, it's been known how to do this for decades. Okay, there's really no magic. Okay, good. So that was the language of refinements, and this is the sort of a formal description of the language of the types, of refinement types. Okay, so we'll have sort of basic types like int, bool, etc., etc. Then you have type variables A, B, C, D, E, etc. And we'll have refined base types. Okay, so x such that x of some base type int such that some predicate, and we'll have refined function types. And this should already give you a clue as to what's going on. I'm going to write function types as x colon t goes to t prime, meaning that in this output type, I want to be able to refer to this input type. So x sort of names the former, and I'm going to be able to refer to the former in the output type. Okay, so that was very abstract. Let's look at some concrete examples. Oh, let's look at some concrete examples. Let's pop back over here. Okay, blah blah blah, type nat, etc., etc. 11, mumble mumble. Hang on, let me make this full screen, shall I? Okay, good. So 6 is a non-zero. That's terribly exciting. Okay, so let me show you some interesting functions. Okay, so here I'm writing a function somewhat violently named die, which is just a wrapper around good old error. Okay, so die takes a message and just calls error on the message. But here's the deal. I've given die, so die is now the first refined function type that I'm showing you. I'm not referring to the input and the output, but what I'm doing is I'm giving the input type a precondition. Okay, so think of this as, it is a precondition, false. And the question you have to ask is, well, what's the value? So by the way, we let you write this underscore, it'll just fill it in from the underlying Haskell type, right? So it knows that die's input type is a string, so you could write this, or if you're lazy, as I often am, oh, it's not a list of strings. There you see it's freaking out. It is not a list of strings, you fool, it says. It is just a string, and now with any luck it'll shut up. Okay, good. Or you just write an underscore there. Okay, good. So what's the value of type string such that false? So the great thing about false is, of course, there's nothing that satisfies false. And sort of pushing that logic a step further, what this means is you should never call this function. Okay, so any calls to this function, game over, right? You should never ever call this function. So which is basically the same as with error, right? You should not call error. If you have to call error, you've lost. Okay, it's game over. So what this means is that now in all those cases where you really hope this never ever happens, you can just put in a die, and if your program type checks, then you know that in fact that function was, the bad thing never happened. So here's an example. Okay, so let's try and write a divide operation. Okay, so divide takes an integer and a divisor, and if the divisor was 0, you sort of die, right? And the normal thing would be to just write undefined or something like that, or call error oops divide by 0. Instead, what I can do is nuke this undefined and replace it with a call divide by 0. Okay. Now with any luck, I should get an error. Why am I not getting an error over here? Damn you. Jostle. Oh. It's not saving, that's why. What?
Where did you give a restricted type to divide?
I have not, which is why I expect an error. I know what's going on. There's a restricted type somewhere hidden in this file. I swear to you. No, it's not there. But well, I just showed it to you. Cheat area. Allow me to copy it up and pop it at the top. Where is the type? Oh, God help us. What is the problem? Nothing to prevent. What's that? Die, false. Oh boy, why is this running aground when I least wanted to? Oh, I know what. There's probably some silly mistake somewhere. Let us to fly check. Fly check list errors. Specified type does not refine Haskell type for refinements. Oh, it's that. It's your fault. It's still this. There we go.
Exactly to plan.
Yeah. Jeez. Okay, here we go. So now when I go down to divide, here we go. This is what I wanted, right? Let's only it up. Here we go. So now you see what it's giving me. Okay, it puts a little red thing there saying, hey, you know what? This does not type check. meaning you were not supposed to call die, but I can patently see that you're calling die over here, right? If I move the mouse here, it'll probably give me some vaguely useful error message. Type mismatch, well, it's not terribly exciting, but inferred type of this string is not a subtype of false, because, well, nothing can really be a subtype of false, okay? So now the question is, how do we fix this particular problem? I have to somehow say, I have to push the precondition burden onto divide and say you should never call divide with a non-zero value, right? With a non-zero, what is it called, divisor. So that would be something like divide. I don't really care about this, but this chap should be non-zero, and I get back an int. Fine, fine, fine. Let's just fill it all in, okay? And now when I do that, this particular error goes away, right? It's like, okay, I understand that this die actually never gets called. Why is that? Because it knows that it knows that the arguments of divide, and I'll explain what this it knows means in just a second when I show you the more formal side of the development. It knows that this fellow is never going to be a 0, and so effectively this branch is dead code, because its assumptions are that it's a non-zero value, and hey, it is 0, that means this never actually happens, right? There's a contradiction in the environment, and this branch is dead code. Now, of course, if you flip the order, then it doesn't work out that way, right? Actually, then it's dead code for a different reason. You end up calling div and then do that. Okay, good. So let's look at a couple of examples. So here, if I call average 2 on xy, that'll type check, right? Because 2 is non-zero. And if I do divide of x plus y plus z by 3, that'll type check naturally. But if I go back to that example where I come here, right? Here, imagine I have x's, which is some list of integers, right? And I want to add up everything in x's, that's the total, and n is the number of elements, and I want to divide the total by n. Now it doesn't like that, because like, well, I don't know that n is non-zero. In fact, it may not be 0 because this length, what if you give me the empty list, okay? So one kind of shady way to fix this would be, let's see what it says. What does it say over here? Can you see this? Probably not. But long story short, what it says is the type that I've inferred is that n is equal to the length of x's. Oh. How does one keep that persistent? In a context where I know that x's has a non-negative length, okay, so greater than or equal to 0, but it's not, it may actually be equal to 0. And so one way we might fix it is by, oh, I haven't told you anything about length yet, have I? But let's just see. If I make it n plus 1, it'll be fine. Right? Because it knows that it's a NAT. If I add 1 to it, then it's all good. But that's kind of a shady thing to do. I mean, what the hell does that mean? It's not even an average. Okay, so let's see how some of this works out, right? So what's the theory over here? How is this really working in practice? The main workhorse, the main sort of technical engine that's underneath is a subtyping judgment. So why is it that I can say 6 is a NAT as well as a non-zero, as well as an even number, etc., right? So in Greek, by the way, should I just skip this and keep moving with the demo, or do you want to see this? No point asking people, they never know what to say. You want to see what? You want to see the Greek? Okay, Greek, fine. This is the Haskell meetup after all. Is that yeah, okay, good. So you have gamma, so the subtyping judgment looks like this. Under an environment gamma, where gamma is going to be a collection of type bindings, the usual type environment, a type T1 is a subtype of T2, right? So what does it mean for a type T1 to be a subtype of T2? For base types, by the way, this basic idea goes back to the mid-90s. It's called predicate subtyping, for those of you who follow this sort of thing, okay, from a proof assistant called PBS. For base types, subtyping is simply the following. Okay, so I can never tell with typing rules, you read them bottom to the top or whatnot, so let's just start at the bottom. If I want to show that in some environment, if I have the following type bindings, xi has the type pi. Let's just throw out what the basic type int bool was, right? Xi is an int such that pi. In such an environment, if I want to prove that a value of some base type b such that q is a subtype of values of base type b such that r, then what you need to prove is the following implication. You need to prove that if I conjoin all the pi's and I take q, then that implies r. Okay, so we'll see some examples in just a second. Okay, or you can read this up or down. So if this condition is valid, then this subtyping holds. Okay, and this is the subtyping for base types, and all values have some type, right? And what we're going to do is, once you have higher order values or lists or functions or so on and so forth, you just use the standard rules for subtyping on those to drill those down into base types. Okay, so I'm not going to show you examples of that. So usual co-contravariance, all that sort of thing, right? I'm not going to show you fancy rules for that. Everything just boils down, in the end, to subtyping on base types. Okay, good. So let's look at a quick example. So remember our old friend Nat. In the empty environment, we don't even need any bindings. I can show that 0, where 0 was the type value equals 0, is a subtype of Nat because it boils down to this logical implication. True and value equals 0 implies value is greater than 0. And you know, these little SMT solvers, which I described, briefly alluded to earlier, will prove these kind of implications without batting an eyelid. Okay? And this is why, because this subtyping holds, I can show that 0, which was formerly of type capital 0, is in fact also a subtype of NAT. Okay, now you can replace NAT with even or whatever, right? Greater than -5, and the same sort of logic works. Okay, I showed you this example already, right? So we have this safe divisor, I have this non-zero, right? This is, think of it as a precondition, so the divisor D has the precondition that is non-zero. And here what happened is if I do 10 safeDiv by n, where n is a NAT, right? So here I'm assuming that n is a NAT, then I end up with a subtyping check that looks like this. In the environment, I get to assume that n is a NAT, and I want to prove that this expression, which has the type value equals n, is a subtype of non-zero. Right? So I need to prove that this subtyping obligation holds. But of course it does not hold because, whoa, if you just read this as implications, then n greater than equal to 0, value equals n, does not imply that value is not equal to 0. Right? But if I replace this with n plus 1, then it all works out, right? N is a NAT, value equals n plus 1 is in fact a subtype of value not equal 0 because this reduces to the following implication, which is valid. Okay? So far so good. This is about as much into the theory as I'm going to get. Okay? So let me show you another example, and that's about all I'm going to show you about how the underlying machinery works. So here's a simple absolute value function. Okay, it's going to take as input some x. If x is greater than 0, it returns x. Otherwise, it returns 0 minus x. Okay? So you might specify a type for it that looks like this. Absolute value takes as input some x, which is an integer, and returns as output a NAT, which is in fact greater than x. So remember how I said you could name the inputs and you could refer to them in the outputs, right? So here it takes an input and returns a value that's greater than x. And how does it do that? So so how does it check that abs in fact behaves like this? Here's what it does, okay? All we're going to do is we'll assume that the input x is an int, and here are the two places where values get returned, x and 0 minus x. And I'm just going to check that in both cases the value that's returned is a subtype of the claimed output type, okay? So I end up with two subtyping obligations. In the first one is from here. When x is an int, and here's the, there's some extra magic going on, which I will describe very fast. I know that this value is returned under the condition where 0 is less than x. So I can strengthen that in my environment. I can, if any of you has had the pleasure of staring at, what is it called, the core that GHC produces, you know that all these things get blown down into case expressions, right? So it creates these little intermediate binders, and in fact, there's an intermediate binder buried inside the core version of this, whose type is x is greater than 0. Okay? So in an environment where x is an int and I know that 0 is less than x, I return as output a value that is equal to x, and I want to prove that this value is a NAT and that it is greater than equal to x. So that's in the then branch. And in the else branch, I get the else condition, value is 0 minus x, okay? And what is that over there? The same output thing, right? And of course, now you do that same subtyping, becomes a formula. Yeah?
I may be jumping ahead, but how does this interact with JDTs where matching on something there can have some really complex effect?
Well, you can, in fact, think of the real question that you're asking is, what if I had some crazy condition over here, right? So what is going on? Why did I suddenly get this, right? And this is a rather profound question. This is no good. Hang on, let's see if I can backtrack. Damn it. So really what's going on, this is a somewhat technical point that I didn't want to get into, but we will see an example slightly later. So really what's going on is, not so much that you know that 0 is greater than x, But what you really know is that in this branch, a certain proposition is true, where the value of that proposition being true means that 0 is greater than x. So if you have some more complicated condition, what that means is you still know that a certain proposition is true, but you don't know what that proposition being true means. That was a very hand-wavy explanation, but I'll try and maybe we'll come back to this later. Okay. Okay, good. Blah 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 blah. Good. So these are the two subtyping obligations. They reduce to these logical implications. If you are very good at arithmetic, which I am not, I confess, you will realize that both of these hold, and so in fact abs has the right time. Question? No, just okay, good. And you will have to just trust my word that this scales up quite nicely. So it's just like abs, really. Come on, who writes functions with abs? But it turns out that this simple thing that I showed you with how the subtyping checks work, they actually, once you just write a type checker, you actually get an inference algorithm quite nicely. I'm going to say quote unquote for free. It was like a PhD thesis, so I guess it's not for free, but at this point it seems like it's for free. And this works quite nicely, and let's just see an example. Okay, so let me, if I click this, will it work? Who knows? But here, let me just make it work by powering this up. Good. So pop, 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 pop. Whoa. This is for the gentleman who wanted big fonts. Okay, so I just showed you the thing for what a divide, right? Here what I'm doing is I'm defining a data type for lists, the usual list data type. There's nothing terribly exciting over here. And I'm writing a few of the usual functions. Map, the usual map. This is fold right. Everyone knows and loves fold right, I hope. A, B, 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 list of A's, you get back a B. Here's fold right's lesser known but equally valuable younger brother, fold right 1. What does fold right 1 do? Fold right 1, you just give it the accumulator, right? A, and you give it a list of A's. It'll suck the first fellow out of the list and just do the fold, right? But this, and then it'll just call fold right starting with the first fellow from the list. So fold right 1, f of c, blah, blah, blah. It'll just call fold right. And now possibly you know why this is grumbling over there, because there's a call to die. Because what else are you going to do if you pass in the empty list, right? So how do we prevent this particular problem? So let me show you how we prevent this particular, how we tell it, don't worry, I promise I will only call fold right 1 with non-empty lists. Okay, so let me just scroll down a little bit and get to that. Wow, damn it, length. No, did I call it length or did I call it size? Here we go. So here's what we do. Okay, so let's just. So what we let you do is we let you write it's just like a Haskell function, right? Size, list of A to int. And size, you get the idea, right? If it's a const, it's 1 plus the size of the tail. If it's a nil, you get back 0. It looks like it's an ordinary Haskell function. It is an ordinary Haskell function, except that I'm making a few restrictions. Okay, that it's a Haskell function where I require that you have one equation for each constructor, for each of the data constructors. Okay, so for const you have one thing, and for nil you have another. Okay, so modulo this, it's a Haskell function. I mean, it is a Haskell function. And I allow you to use size as inside the refinements, okay, by declaring size to be a measure. Yes?
What if I write size cxxs equals 1 plus size
cxxs?
Yeah.
It would not like you. And if we have time, we shall see that in the end. So notice, in fact, why you can't notice from the screenshot that's over here, but if I scroll up to the top, you will notice how there is this little command line flag. Oh, I should not have. There's a little flag at the top, no termination, right? So if I disable that, then various things start grumbling. And we'll see that in the end. So you can't write things like that. Or you can, but you can't use it as a measure then.
But it's just requiring that your function be structurally recursive.
That's exactly it. Okay. So where were we? Size. Fantastic. So now that I have size, I can now go to town by writing refinements over size. So let's head up to our old friend fold R1. Where did fold R1 go? Here we go. Fold R1. Fantastic. So fold R1, my favorite way of writing refinements is to start with the Haskell type, wrap little comments around it, and then just say value is a list of A's such that size V is greater than 0. Okay? And hallelujah, okay, that particular red thing has gone away. Okay? So far so good? And why is that? Because, well, we know that it's the same thing. It's just like the thing for divide, right? Remember for divide, I said if it's non-zero or something like that. And then in the case where it was a 0, that's a contradiction. Here I get the contradiction because the size of nil is equal to 0. And yet I tell you that in the environment, whatever this list is, Z's, has length strictly greater than 0. So there's your contradiction. And therefore, you can be a subtype of false, right? If the environment is a contradiction. Yeah.
So I assume now we could remove the end case and it would be fine, right?
The which case?
The end case, the second case, right?
Second case of what?
Fold R1.
You could just comment it out, you mean?
Right, yeah.
So what if we commented this out?
That would be fine, right?
Yes.
Okay, but with the old type, would Liquid Haskell complain?
Excellent. I should just put this into the demo because people always ask this. Okay, good. So let's just blow out the old type by commenting it out. Okay, and you see, in fact, there is no complaint. And so you're like, well, that's kind of shady. But if you really wanted it to complain, you could go back up here, and it sounds like. And there you go. Okay, so it's going to say, I don't like this. And really what's happened over here is for all the missing cases, I mean, for those of you who know a little bit about how GHC works, it actually fills out all the cases, right? And it basically calls the equivalent of die. And so that's all we're doing. We're like, okay, we'll treat those as falses. There's no magic here. Okay, fantastic. Question? Yeah.
What if size was a higher order function data could be in a parameter?
There's no higher order functions in the measures. Right? So it's a very restricted subset that I will describe in just a second. Right? So remember what I said, you have one equation for each constructor, and the definition of the equation is essentially an expression that belongs in the refinement logic. Okay? Okay, and we'll see how it all gets desugared, etc., etc. So let me not do this because who knows what consequences it will have. But let's just go down. And let's look at a slightly more interesting function. Okay, so weighted average. So I'm continuing with the average motif. Here's what's going on. Okay, so I'm going to take in a list of weights and numbers, and I'm going to compute a total. And total is just, for each weight and number, multiply the weight with the number. For each, what is the other thing? Each of the weights, just add them up, and then just do the division, right? And so now what it's grumbling is the usual thing. If I put the mouse over here, it's a call to divide, and so it's the usual thing. I don't know, it's a value that's equal to weights. That's all I can say. I don't know that it's not equal to 0. Okay, so that's the error. So how do we get it to shut up about this, right? It's like, no, trust me, it's not going to be 0. Well, first of all, we have to figure out what a reasonable precondition is. Okay, so one attempt would be something like this. I'm going to say that all the weights are positive. Okay, so weighted average takes as input a list of, let's just say a pair of posses, okay, and returns whatever, returns some integer. Will that help? Oh, look, so that's interesting. So now the error has gotten shifted to someplace else. So that's pretty interesting. So I wonder, can anyone comment on why this may have happened? Like, what's going on here? So why is weights, how does it magically know that weights must be non-negative, must be strictly positive now? Can you guess? Can anyone guess? If I call fold right 1, and I'm just doing plus, so plus is a pretty convenient function. Let's see if it will tell us the type of plus. It won't, damn you. But maybe it'll tell us the type of fold right 1. Whoa, it won't. Oh, I have to probably make the fonts a little smaller. Here we go. Maybe you can see this. So what it's saying is that at this particular call site, I have specialized the type of fold right 1 to be pos, arrow, pos, arrow, pos. You give me a list of posses, because that's what all the weights were, right? Remember, it's a list of posses. I mean, once you suck out the weight component, and you will get back a pos. And how does it know that? Because that's just the type of fold right 1, right? A to A to A, list of A's, you get back an A. So it's essentially solved the A's out to be pos, and therefore it's guaranteed that in this particular case, sum always takes a list of posses and returns a pos. And therefore at this point, weights and total are both pos. Okay? So then why is it grumbling over here? So sorry, was there a question? I thought somebody had a dissenting opinion or something. Yes.
Again, I feel like I'm the dissenting.
Yes, yes.
There's some magic here, right? I mean, you have to sort of tell plus that you can turn positive to positive.
I didn't have to tell plus anything. So let me tell you what I've told you about, what it knows about plus. This is kind of shady, but...
Oh yes, okay.
What? You figured it out?
Yeah, okay, I get it.
That's great.
So I mean,
It's subtyping at work, really. So what's, oh, come on, what do you know about plus, for God's sake? Why will you not work? Grind furiously. There we go, okay. Oh, it's GHC has done this to us. It's just sliced out the plus. Let's see if this works. Here we go. Okay, that's actually wrong. But roughly speaking, the type of plus is x1 int, x2 int, value equals x1 plus x2. Okay? And if you do the math, that is a subtype of pos arrow, pos arrow, pos. And of course, you don't have to do the math. The machine is doing the math over here, right? It's a subtype of many different things. What's that? Yes. Modulo of this particular quirk that you raised. Yeah, assuming the integers go on forever. Okay. But at this point, I personally was rather surprised that there was an error at the call to sum. And let's see what that's all about. So what it says is type mismatch, blah, blah, blah. Sum has some type, but is not a subtype of the required type. Size must be strictly greater than 0. Okay, so remember, sum calls for write 1. And for write 1 requires lists that are greater than whatever, non-empty lists. And how do we know that the lists are non-empty? Nothing over here tells me that the lists are non-empty. And so we have to sort of jog back up and say, oh, right, yes. I promise to call you with non-empty lists. Size v is greater than 0. Okay. It's still not happy. Now what do we do? Can you guess? Can anybody guess what the problem is? Where are we losing this non-emptiness fact? Exactly. The type to map doesn't tell us anything about the type of the output, right? It says for all A to B, list of A is a list of B's. It doesn't tell me that the output type, the output list actually has as many elements as the input list. And so let us jog back up to our friend map and give it the relevant type. Okay, so map takes a blah, blah, blah. I'm going to name this, let's call it X's, which is a list of A's. And I get back as output a list of B's whose size is equal to the list X's. And then I close that. And with any luck, okay, it's all good now, right? Because I know that if the input list was non-empty, then the output list was.
So some people would be unhappy that you had to do that, though, right? That it couldn't automatically figure out that that function was size preserving. Right?
So that is a good point, but I should say I've deliberately sort of crippled it over here so that it did not infer that. Okay. There are various ways where it would actually figure that out on its own. But since that doesn't always work, in general it can't figure out whatever magic thing you want. Here, I don't want to give a false impression, right? Here's an example where I really need this information from map, and so you have to go back and strengthen it. Yeah?
So, could you go back to where you gave the type to size, or said size was a measure?
Yes.
So, you said size was a measure, and that did something sort of magical. And you've now used it in types a bunch of times, but you haven't actually used size. Why do you define this thing you use in your types, size, in terms of Haskell code you never actually use, instead of in your comments at some point?
You mean, when you say I haven't used size, you mean I haven't used it in my program?
If you erased your comments, size would be gone.
If I erase these comments, size would
There's no
be gone.
uses of size so far. You could call it, but you haven't.
You type checked with it, but it's not executable code.
Well, it is executable code, it's just never called.
Well, yeah.
So why is the way you structured this thing requiring you to write?
Oh, it's absolutely not. Oh, I see your point. I see your point. This is purely a convenience. So this is because people would always like, oh, it's so strange, why is it a separate? In reality, and in fact, even the thing I'm showing you right now is very, very fragile. In reality, this whole thing would be wrapped inside comments. Maybe this would make you feel a little happier. Oop.
Okay, so you can't do that.
Yes. In fact, not only you can do that, you should do that, because this happens to be a lot more robust. Oh, I hate misaligned equals, sorry. Okay. Okay, so in reality, this is really what's happening. Okay, so we're just giving it to you as a convenience. If you happen to have these functions lying around and you would want to call them externally, then fine, go ahead and just use them as measures, right? But really, for the vast majority of cases, we end up writing them in these curly blocks.
It's still giving you a parse error.
Ah, yes. Something about parentheses, I feel. Oh, just the fact that I haven't saved the file. Please, please, go away.
You've got the beginning of the line.
It's like, who knows? I'm done with this file anyway.
Oh wait, that's saying it's an error.
Oh, I know what it is. This is like I can't for the life of me write a parser. Sorry. Oh, of course. Never mind. There was a question somewhere else. Maybe Cody had a question. I forget. Okay, good. Why does this not work? Okay, good. So, and by the way, you can do the usual things with. Let me get my dig into the. You know, you can do the usual things one does with size too, right? Where I have append and I. But I may as well do this. I find this quite funny. You can say append. It takes a list x's. It takes a list y's. And it returns as output a list, so lazy, such that size v is size x's plus size y's. Right? This is the, it's the usual kind of thing one does. But unlike in the fully dependently typed systems, you can also do this. You can also replace the y's and the x's, and it doesn't matter because the underlying decision procedure is not unification. Okay, and so it turns out that since the decision procedure actually understands arithmetic, you don't have to worry so much about things like computativity and so on and so forth, right? But anyway, this is a kind of inside joke. Never mind. Limitations, should I really get into that? I guess I could, but we definitely won't get to the bits I want to talk about. Here's a really extreme thing. For those of you who know this, you can also write list append using fold right. Do you know this trick? This is the one where you do a fold right starting with y's, the thing you want to append to, and then you just fold over x's. And so at each step you just keep adding one more thing. And so you would like to be able to say that at the end of the day I get back, the output list is in fact has the same length as concatenating the inputs and the outputs. But we can't, because the type that we have for fold right is just this very boring type, which is ABA, go away, ABA list of, and there's nothing in there that tells me that I actually run fold right over the entire list y's and so on and so forth, right? So it seems like the kind of thing Cody would want. It's a very higher order specification for fold right, and we can't seem to do it. But of course we can, but I won't have time to talk about it. Maybe I will at the end. We shall see. But let me, I think we were supposed to take a break at some point. It is not 9 o'clock, right? It's actually 8 o'clock. Please tell me I've not been talking for 2 hours. That would be scary. Let me just explain a little bit about how this works. So what's going on with this whole size thing? Okay, so blah, blah, blah. Let's just see how this whole business of measures actually worked. Okay? So here's what I did. I defined a type list. I wrote something that was measure size, and I've been very careful. Notice I have one data constructor over here, and each of these expressions on the right-hand side of the equation also belongs in my refinement logic. 0, 1 plus. This is, by the way, remember those uninterpreted functions? That's where they come in. Okay? So here's what's really happening. When you write something like this, internally it gets desugared or converted into something like this. Okay? So what's going on is I'm strengthening the types of the data constructors so that essentially I'm going to say nil or n has the type list of a such that size v equals 0. Okay? And cons has the type you give me an a, you give me some tail, and the size of the result, size v, is 1 plus size t. Okay? So it's a fairly straightforward exercise to go from definitions like this into strengthened data constructors like this. Okay? If you squint a little, it's not terribly magical. So what? What's so great about using the data constructors? What's so great about the data constructors is, remember how I said I really want the decision procedure to use only queries over a decidable logic, okay? Which means the decision procedure can't understand what the hell size is. It's a recursive function, okay? That way lies undecidability, okay? So once we're in the refinements, size v is an uninterpreted function, which means, let me explain, a function f is uninterpreted if, for any x and y, the only thing you know about the function is that if x is equal to y, then f of x is equal to f of y. You know nothing else. Okay, so for size, if I know x is equal to y, I know size of x is equal to size of y. I know nothing else. Okay? Yet, how is it that we come up with all these fantastic facts about append and so on? It's those data constructors. So check it out. What we're going to do is we're just going to assert those facts when we do the folds and the unfolds. Okay, so when GHC sort of desugars the program, it's going to do all the work for us. So what do I mean by a fold? It's the application of the data constructor. So when I say C cons of x and y, because I've turned the data constructor into a function, right, and I've given that function the type that says that its output has length or has size 1 greater than the size of y, I know that the type of z is size v, which is equal to 1 plus size of y. Right? It's just a function call. I'm just inlining the type of.
I'm a little confused.
Yep.
Why don't we just add sort of assert that size obeys those equations?
Because that's not decidable. Because then it's universally quantified with recursive equations, and you're outside the happy world in which I like to live. Okay? But you're right, that's the equivalent thing you could do, but that's not the space I want to be in. Because then you're making queries to the, what is the expression? You're cashing checks that you can't, you know what I'm talking about, right? So I like to ask SMT solvers questions where they will say yes or no, and not maybe. That's why. Okay? So that's what I do at folds, and the reverse thing happens when I do an unfold. So an unfold is when I say case z off. If I say case z off, if it's a nil, then I know that, in this case I can strengthen the environment and just say size v is equal to 0, but exactly that's what's going on, either way, right? If I say cons xy, then at this point I know, size of v is 1 plus size of y, where y was the unfolded thing. That's it, it's a total syntactic hack, right? I just take those weird measure definitions, I tuck their types inside the data constructors, and then as I use the constructors by folding or at unfolding, I just belch out those equations, and that's it. Yeah?
This is sort of like the refinements that you get with GADTs, but it's more flexible because you're feeding it into an SMT solver.
That's exactly that's a very nice way of putting it. That's in fact exactly what's going on. And what we'll see in a second is you get two benefits. So one is you get to feed them into an SMT solver, and two is that you can actually write multiple refinements, multiple of these measures for the same data constructor. So one of the things that I find unpleasant about GADTs is if you want to talk about invariance or various things like lengths or whatnot, you have to know what properties you care about and index your data structure up front. Okay? So let me just, wait, I already showed you this. So let's skip that.
Like 5 different indices or something.
Exactly. So, well, it's worse. I mean, all your constructors change if I want to add some new property that I care about, right? While really what I want to say is, look, here is the type, and it is independent of the indices, and you can just keep layering on newer properties as you care, as you like. Okay, so here's an example. For example, if I just have my same list, so I already showed you a thing for the size. Here's one for is the list empty or not, right? So an is null measure. Is null of nil is, well, true. Is null of cons is false, right? And all that happens is, it's that same data constructor trick. If I only had one measure, I would get these. But if I have two measures, well, it's logic. When you have AND, you can just keep slapping more and more of them on. Okay? And this turns out to be a very handy thing. So let me show you one of my favorite uses of measures. What was that thing called again? 0, 1 elements. Okay, let's blow up the fonts. So here's a fun one. It's the same list, but now I'm going to track inside the list the set of elements that are in the list. Okay, so not just something boring like the length, which is an integer, or is it null or not. It turns out that the theory of sets, which I did not show on that slide, is also nicely decidable, right? So you can make queries about it as long as there are no quantifiers. So for the empty list, it's just the empty set. Don't pay no attention to the 0. If it's a list x cons x's, it's just a singleton x cons with the elements of x. Right? That's it. Okay, and I'm going to call that measure lms. And here are a few handy aliases. So EQ elements just means the elements of x's is equal to the elements of y's. Union means the elements of x's is the union of the elements of y's and z's. Okay? So now you can write specifications like this. If you take append, it takes two lists x's and y's and it returns a list whose elements are actually the union of the elements of x's and y's. Okay? Or, well, reverse does the usual thing, right? If you reverse, you should not change the set of elements, so you get that. Let's ignore that. Oh, here's a fun one. Here's one I like a lot. This is from xmonad, which maybe some of you have used. I used to use it a lot, except that you can't get it to work on the Mac, or I can't get it to work on the Mac. So one of the things that xmonad has is it has a data type in it called a stack set, which is your list of windows essentially. And one of the crucial invariants they want to maintain is that there are no duplicates in that list. Okay? So here's a fun little measure that takes a list and it will tell you whether or not there are any duplicates in that list. Okay, so obviously the empty list there are no duplicates. And if you have the list x const x's, there are no duplicates as long as there are no duplicates in x's and x is not a member of the elements of the tail x's. Right? So this is a recursive function you would write. Yeah?
So you had a different version of append that said it returned the union of the elements?
Oh, and that did not work. This one over here.
Well, no. Okay, so you might want to have a refinement of append that has the link adding and the one that has the element unioning. You have to write a single type that has both of those if you give two refinement types?
Or you could just add, you could say this and that.
Okay.
You would say size of v equals size of x's plus size of y's, and elements of v equals union of the elements.
Right, but do you have to give it in a single type? Or
So right now you have to give it in a single type, but it would be pretty straightforward to actually just let you write multiple signatures and then combine them.
Okay.
But right now you have to write a single type. Yeah?
What's the notion of equality that's used here in the no duplications? Is that the equality that would be defined by instantiating the eq type class, or is that some more magical equality?
It is in fact a magical equality. Okay. Or put another way, we assume that your instantiation of eq is kosher, right? So it basically satisfies the usual laws, symmetry, transitivity, reflexivity.
But it doesn't necessarily have to be structural then?
It doesn't have to be structural.
Okay.
Okay?
Cool.
Okay, but this is, so the logic just assumes those three things, right? So the logical equality is just, transitivity, symmetry, and reflexivity.
It's an equivalence relation.
Exactly.
The prelude has instances of eq that are not equivalence relations. Nan is not equal to nan for floating points.
Right. So yes. So this breaks down there, and I'm not going to worry too much about this because life would be short. Okay. So where was I? So no duplicates, right? So here's this measure describes this, and here's a function from the prelude since you brought it up. It's called nub. I've never understood why it's called nub, but it's called nub. You can look it up. And it takes a list x's, which is an instance of EQ, and it sort of walks over the list and throws out all the duplicates, right? And so the property that you'd want is that x's, that nub returns as output a list v, which has no duplicates, and which otherwise has the same set of elements as the input list x's. Okay? And here is one of those examples where the guard is actually quite non-trivial, right? If x lm l, where lm is a function call, I mean lm calls this thing over here. And this sort of illustrates roughly what's going on. So lm just returns a boolean, okay? And we think of booleans as just an ADT, right? That is true and false. But the prop v is a mapping from booleans true or false to real logical truth or falsehood. And what we say is that prop v is true if and only if x in fact belongs in the set of elements given by y's, right? So that's the type of lm. And you throw it all up and it works out quite nicely. And there was a break that was promised, and I will give it to you in just a second. Let me just show you one last example, which was, hey, why is this not crashing? I really wanted this to have an error. Oh, I bet because I've created one of those, let's see, there's some silly error it's irritating when some silly error blocks the real error. Oh no, that's not at all what it is. Oh, it's not at all that. Let's see, did I already? Oh, that's why I was supposed to have deleted it. Here we go. So remember the thing I alluded to earlier where you have a key value map and you have some key, you're trying to find it in the map. And yes, you could always just or, what is it, is just the Ocampo one or the Haskell one? Justice Haskell, right? Sorry, I was getting mixed up. You could always maybe it up, right? But let's say you're not maybeing it up. So I have key and a list of key values. If key is equal to k, then you get a v. Otherwise, you recurse up over the tail. And if you hit the end, whoops, you're out of luck. You call die. Okay? And how shall we get this die never to happen? Well, I must promise to call find always with keys that I know for sure belong in the map, right? In the association list. And here's how I might do it. I would, in fact, describe the set of keys that are inside an association list. So I take a list of ABs, and I give you back a set of A's, which is how you think. Empty is empty, KV, it's a union of the first element of KV and whatever's in the tail. And poppity pop. And so once I do this, I can write just a shorthand. Valid key, K is a valid key in M if K actually belongs in the keys of M. And now since I have cunningly already copied it into my buffer, I can paste it in over there. I have find, takes a key K, and a map M such that valid key of Km, and there you go. Okay, and it's the same thing. I know the nil will never happen because I was told up front that K is in fact in the list, and the empty list has K cannot be in the empty list, right? There's another funner example of this, but I think I will stop at this point for a break. Should we take a break? What is the plan? Yeah? Should we take a quick break? Okay, let's take a quick break, and then we will return presently. Oh, you already made my point. Maybe I'll just... Oh, there we go. Blah, blah, blah. Okay. I've shown you a whole bunch of really tiny little examples. I will show you some slightly less tiny examples now. And there were really two, but in the interest of time, I think I'll show you the more interesting ones. So these are at two ends of the spectrum, right? Red-black trees are this kind of, everybody knows and loves red-black trees. It's really nice how we can do it with measures, and it's the usual red-black color, height, mumble, right? It's there. It's fine. You can look it up. I think I'll just skip it in the interest of time. Instead of the last 2 days, I've been hacking up this. I mean, we did these benchmarks a long time ago, but I think I've distilled it into a nice kind of small little nugget that I can explain to you, which is about low-level memory safety, or some level of low-level memory safety in Haskell, and how one can why do you even talk about low-level memory? How do you talk about low-level memory, and so on, right? So I'm going to say heartbleed in quotes, just because it's not really heartbleed, right? But it's in quotes. I heard somebody mention this, which is, fancy languages like Haskell, of course, rest upon the rock-steady foundations of C. And, you could make little mistakes in how you use these foundations, and, you could end up with little problems. So here is a string truncation function called chop. Very creatively takes a string and int and gives you back a string. It's basically the same thing I showed you at the beginning, right? So chop takes an s and an n, and it gives you back an s prime. And all of these fellows, pack, unsafe, take, and unpack, are from the bytestring library. Okay, so data, bytestring, whatever, right? And so here all I'm doing is I take the string s and I pack it and I get some bytestring b. I call unsafe take n on b, which just sucks out the first n characters. I get back some b prime, and then I unpack b prime and I give it back to you as a string. Okay? So you could try, so this is roughly what happens, right? So if, I don't know if all of you know how bytestring works, but the reason bytestring is very, very fast is underneath the hood it's all implemented with C and just using sort of raw buffers of memory with pointers and so on, right? So if I use the string Ranjit loves burritos as the, I call chop with Ranjit loves burritos, right? And I give it heartbleed of, oh sorry, this should be chop, not heartbleed. Whatever, x of 10, then it'll give me back Ranjit love, because it's super fast. The way bystring works is it just sort of jogs the pointer by 10, right? And so it'll give me this, and then there you go, Ranjit love, right? But if I use a somewhat longer, instead of 10, I make this 30, then it'll actually go ahead and tell me whatever's in the contents of the memory after where Ranjit loves burritos ends. Okay, so you can try this at home if you like. I don't know why you do it, but okay. So how is it that we can somehow get the compiler or build a tool that would prevent me from doing this kind of thing? Right? What is it going to take in order to block this sort of thing from happening at compile time? Okay, so what we're going to do is think of it as the slogan, if you wish, is types against overflows. Is we're going to have to start at the very bottom, right? So I'm going to specify and verify types for the low-level pointer API. Okay, and I'll show you what I mean by that in just a second. Then the library-level byte string API. And then finally the application API. By application here, I just mean the chop function, right? But that's what I mean by the application, okay? And the idea is that at each level, errors are going to be prevented by the types that I wrote at the previous level. Of course, in this case, there is no previous level because this calls out to the machine. That is to say C, right? So we have, so in a sense, the trusted computing base is the types that I'm going to give to these fellows over here. But hopefully this API is sufficiently small and some other very clever person has made sure that your C functions actually implement this API. These we're just going to have to trust. Okay, so let me walk you through what these three quote-unquote APIs look like and what the refinement types will look like. Okay, good. So what is the pointer API? In a nutshell, you have two kinds of pointers, right? So you have this PTR of A, which are your raw pointers, and then foreign pointers, which are essentially pointers that you can export to and from C, roughly speaking, right? And the operations on these pointers are the following. You can read, so given a raw pointer, pointer A, you can read whatever's at that pointer. You can write, so given a pointer A and an A, you can do an I/O operation, and that sort of updates the contents of the memory. There's also, by the way, a storable type class here that I'm dropping, which is for brevity. And here's the trick. You can do pointer arithmetic, right? So the reason byte string and text and so on are fast is because they do a whole bunch of pointer arithmetic to actually access the contents of memory. So roughly speaking, I'm simplifying things over here. Plus pointer takes a pointer, takes a number, and bumps that pointer up by that, that many bytes to make it point to wherever. Okay, good. All right. How does someone actually allocate, and how do you get your hands on a pointer? Well, it's actually called malloc foreign pointer bytes. It's some much longer name that I'm just calling malloc for the purposes of this talk, right? So malloc takes an integer and gives you back a chunk of memory of that particular size, and it gives you a pointer to the beginning of that block of memory, right? And the way you actually use this foreign pointer is with this nice little thing called with foreign pointer. It's actually something longer, but this will do for us. With foreign pointer, it takes a foreign pointer. Remember, the foreign pointer is really just a wrapper around a pointer. So it unwraps that foreign pointer, and so you give it the pointer, you give it a function that takes a pointer as input and performs some I/O action, and finally you get as output the I/O action. And what this function does, it takes your foreign pointer, it unwraps it, calls your function on it, and whatever that returns, you get back as your IOP. Right? So this is the kind of low-level, all of these are implemented in C or in the runtime, right? So there's not much we can do about these. Okay, so here's an example of how one would use the API. So it's not the world's most exciting function, but it is what it is. So 0, 4, it allocates a block and writes 4 zeros into it. Okay, 4 zeros of type word 8 if you really want to know. So it creates calls malloc of 4, right? So it creates a block of size 4. And then it calls this with foreign pointer, it takes the foreign pointer, and here's the function, right? This is the pointer, right? This is the foreign pointer, this is the unwrapped pointer. It does, what does it do? It does poke, 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 poke at the offset 0, at the offset 1, at the offset 2, and at the offset 3, it writes in 0. And then having done all these pokes, it returns you the FP. Okay? So far so good, I hope I haven't lost anyone. Now, your canonical overflow would happen if you, wait, why is there no canonical overflow? How annoying. Your canonical, well, you can always make it happen. LHS. These slides are also generated by Liquid Haskell. So here we go. 0, 4. If I don't like the slides, by God, I will change it. Here we go. So this is that same slide. And if I replace this, see this begin code, if I make this 3 be a 30, then unpleasant things should happen. Okay, so it's like, I don't like this. Okay, this is clearly out of bounds. Okay, so wait, how did that happen? Okay, so let's go back and see how we might tweak the API in order to actually prevent these kinds of out of bounds accesses. Okay, so what we're going to do is, we're going to take that low level API and we just have a refined API, right? So I'm going to refine the pointers to track the size of the buffer that remains at the, at wherever the pointer is pointing. And then I'm going to refine the operations, the peaks and the pokes and the mallocs and what have you, so that those sizes get tracked. Okay? So here we go. So I'm going to create two measures. I'm going to create a measure called plen, which takes a pointer and tells you how much space remains in the buffer pointed to by that pointer, and the same thing called an fplen, right, which works for foreign pointers. Okay? And here are some little abbreviations. So type pointer n is a pointer to a buffer with exactly n bytes, and the same for foreign pointer. It makes the signatures a little more pleasant. Yeah?
How are you actually going to implement those measures?
Excellent question. In fact, we're not. Because we cannot implement them, right? In the end, they're implemented by the runtime.
Oh, and they're just uninterpreted functions?
They're just uninterpreted functions.
Right.
But that's a great question, okay? Fantastic. We can't actually implement them in any way. They're just these funny, they're what in the program verification world are colorfully called ghost functions, okay? Okay, but we're going to quote unquote implement them in our refined API, right? We can have them pop up over here. You can, by the way, so they're called ghost functions, and in the types world, there's a somewhat equivalent notion called a phantom type. It's a roughly similar idea, right? Okay, so here's the idea. I'm going to tweak the type of malloc so that it doesn't just take an int and return a foreign pointer. It actually takes a nat, n, and it gives me back a foreign pointer that points into a region with n bytes. Okay, so it's a foreign pointer a of n. And this is just, it's the same, I'm just writing it in this syntax. It folds out into those curly brackets and whatnot, right? So that's the type of malloc. Here's the type of with foreign pointer. You give it an FP, a foreign pointer, and now here's the trick. The function that you give it is going to get called with a pointer whose length is exactly equal to whatever the size of this FP was, right? Because it's just the unwrapped function. So if you gave me a foreign pointer with 10 bytes remaining in its buffer, then the function that you gave me to then call on the unwrapped pointer will be called on a pointer with exactly those 10 bytes. Okay, so that's how this unwrapping thing works. And so that's why it's so convenient to work with the types, because these kind of higher order specifications work out quite nicely. IOB, and then you have this IOB. So we're just tweaking, I'm just naming the foreign pointer, and I'm saying this action is going to get called on a pointer with exactly as many bytes remaining as the input foreign pointer. We're going to tweak the type of plus pointer to track how much space remains, right? So if I have plus pointer, when it takes us input a pointer, it takes an offset and then bumps up the pointer by that offset. Roughly speaking, here's what I'm going to do. I'm going to take the pointer p. The offset has to be a nat, so I'm just simplifying things a little bit over here, but I can't say go back 5 bytes, right? So I'm just saying this has to be a nat. And furthermore, I'm preventing you from giving me a nat that overflows the bounds of the pointer p, right? So if the pointer p had 10 bytes remaining, if the p-len of p was 10, then the offset that you give me must be less than or equal to 10. Like you can't go too far off the deep end. And finally, you get back as output a pointer to a region B, right? Whose length, oh crap, this should be a p and not a, crap, hold on. Anyway, this should be a p-len of p minus the offset. Right? So if you had 10 bytes remaining, and you move the pointer by some offset O, now you have 10 minus O bytes remaining at the target pointer. Does that make sense? Okay? So far so good? Okay, fantastic. Having done all this machinery for malloc and plus pointer and whatnot, now to prevent my buffer overflows, what I want to make sure is that when you do reads and writes, you write into regions that have some remaining space, right? You haven't gone off the deep end. So it looks roughly like this. Peak takes as input a pointer, but there must be non-zero bytes left inside that buffer. Okay? And the same for poke. Right? Takes a pointer, and you must have some non-zero bytes. Okay? So you couldn't have gone off the deep end. And that's pretty much it. Once I give you all these signatures, now you see at this particular point, it's grumbling. It says you can't do this plus pointer by 5 because, well, why don't we go back to Emacs and maybe we'll get an error message. Or 30 for that matter. Here we go. Well, this is this. Oh, here we go. Oh, can you see this? Blah over there, something plus 30 is not a subtype of must be less than the p-len of p. Right? So remember in this case, what I know is that p is a pointer whose p-len is if you chase through this grisly thing, somewhere or the other a 4 will appear. Here we go. Is equal to b, 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 b. Well, somewhere or the other, it is constrained to be 4, right? If you follow this chain of logic. Yeah.
Question from one step ago. Are the types that you're peeking and probing constrained to be 1 byte in size?
They are not. So this is one of the things I'm actually simplifying, because the plus pointer takes whatever the A is and multiplies it appropriately. Right? So for the purposes of this talk, yes, let's just say they're all constrained to be exactly, you have exactly 1 unit of space. Really what it's going to do is, the plus pointer is, if I recall correctly, it takes the storable of, it uses the dictionary for whatever the A is that the pointer is pointing to, and it actually bumps up the pointer by some constant factor determined by that storable. What's that?
Plus pointer doesn't take storable.
Then how does it work?
Common mistake.
Let's just look it up. We can always just look this up.
No,
I
it's pointer
think,
A to int to pointer B.
Yeah, let's include.
Yeah, absolutely. It's just like, it's bytes. It's absolutely terrible.
Here we go. So it is in fact low-level bytes.
Yep.
So, sorry.
Unsafe, whatever. I don't get it. I mean, is pointer A to pointer B?
Yep.
Yeah.
Because it's usually used to do things like you use plus pointer to compute an offset to a member inside of a structure, et cetera, rather than to move over an integral number of elements.
So, by the way, so which is an important point here, because I'm not guaranteeing to you any kind of type safety about that, right? All I'm telling you is that if you allocated 100 bytes, you are just wiggling the pointer up and down within those 100 bytes.
Yep.
I'm not telling you anything about the layout of objects inside those 100 bytes. Yeah?
Are we missing, these are taking ints, aren't we missing checks to make sure the ints are non-negative?
Oh, I put that in, if you recall.
Where? Can you see it?
Oh, sorry, I went back too fast. Give me a second. We're almost there. So close. Here we go. There we go. So this is the fellow that insists that the plus pointer always takes nats. And the malloc similarly, here we go. Malloc also takes nats. So everything's a nat. There's no messing around with it. And by the way, right. Okay. So far so good?
Was PLAN a nat as well?
PLAN, well, it's a subtle question. PLAN just returns an int.
Okay.
But the way we've set things up with plus pointer, the reason I put this particular constraint in is to ensure exactly the thing you mentioned, which is that PLAN always remains positive or not negative. Okay? Because otherwise, why do you really need that as a pen box?
Right.
Okay, so I'm strengthening the precondition to give me that. I don't know why we do that. Okay. Read and write. Oh wait, we already did all this stuff. Peek, poke, mumble, mumble. Okay, good. So far so good, right? So now all it knows is at this point the PLAN of P is 4. That it's got, so all of this is tucked away in the environment somewhere, which is why since I have 5 over here, it does not like it. Okay? And similar, I already showed you this. Okay, good. So that's the low-level API. Now let's see, how does one then build byte strings on top of this API? Right? So you start with this peek and poke and just these pointer and foreign pointer. What is a byte string? Okay, so here's a byte string in a picture. Okay, a byte string is something that looks like this. Ignore the bangs. The real thing has the bangs. We don't have to worry about the bangs. So a byte string is a triple of a pointer. So a pointer into a foreign pointer to a word 8. That's not important. It's an offset into the region pointed to by the pointer, and a b-len, a length parameter, a length field. Okay, so roughly speaking, what you might have is something like, imagine this whole tape is your memory. The pointer points over here. You have some offset of whatever, 7, and then starting at this offset, you have 10 bytes, which is your length. Okay, and this offset thing is used, for example, if you want to compute suffixes, it's quite convenient, right? You just bump up the offset, and so on. And similarly, if you want to chop off bits at the end, you just shrink the length. Okay, so that's why they have this offset as well as a length field. That's how they set these things up. Okay, but there are some interesting invariants that are somewhat in this picture, which is that the sum of the offset and the length must be at least equal to the size of the region that the pointer was referring to. Right? There's some sort of basic sanity that you have to maintain. So that looks something like this. Your offset must point into, well, you have some pointer, the payload pointer as they call it. Your offset must be within the FP-len of the payload pointer. So if you allocated 100 bytes, your offset can't be 298. Okay, it must be less than 100. And furthermore, your length must be such that the length plus the offset is still within the bounds of the allocated region. Okay? And all of these you can specify just by defining this refined data type for the byte string, where you slap on these extra constraints. Okay? And now what's going to happen is, it essentially makes it, once you do this, you cannot create invalid byte strings. Okay? It's just, this thing about make illegal states unrepresentable. Once you do this, you can't play games. So here are some examples. So here's a good byte string. I do a malloc of 5, and then I create a byte string with that pointer. The offset is 0, and the length is 5. Right? This is legit. I could also create a byte string. I could malloc 5, and then maybe I don't actually use all the 5 bytes. I just start at the offset 2, and I take then the next 3 elements. Okay, so the first 2 bytes have basically gone waste. In the first case, it's a byte string of length 5. In the second case, it's a byte string of length 3. Okay, even though the malloc is 5. But if you try and play games like this, imagine I do a malloc of 3, right? I only create a buffer with 3 bytes, and then I try to pretend that the length of my byte string is 10. You probably can't see this 10. Then it won't like you, right? So it flags an error. Similarly, if I create a buffer of size 3, and I say, oh, starting at the offset 2, give me 2 more bytes, again, that's an overflow, right? That's not kosher, because that exceeds the 3. Okay, so all of these are no longer represented. Okay, good. So that's the basic byte string, just the data type. So of course, now no one creates byte strings in this particular style. The way one creates byte strings is roughly, they have a little function called create, which is a kind of wrapper around the with foreign pointer. It looks roughly like this. So if you want to create a byte string of size n, you pass in a parameter n, which is going to be a nat, and a filling function. Okay, and what the filling function does is, the old unsafe perform IO, but what do? Well, you malloc, you create the byte string, and then you call with foreign pointer with this filling function. Okay? And then you return as output the byte string. So with the payload fp, offset of 0, and the length is n. Okay? So far so good? Oh, there is no error. Where is the error? There's no error. Create. Da, 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 da. Oh, that's why there's no error. Oh, because I gave the signature, right? So if we drop that particular signature, then with any luck, where are the errors? Please, no error. Was the error not there? The error comes somewhere else. It's a bit surprising. Malloc with foreign pointer. Actually, no, everything here is legit. No, it's totally not legit. Huh. Save. Finally. Okay, there you go. There's the error. Okay, so if I comment the signature out, I can't just call create with any random number. Remember, malloc takes nats as input, right? And so if I nuke that signature, then it's going to, I don't like this n. Malloc requires a nat, but this is not necessarily a nat. So you appease it by saying, yes, I promise I will only call create with nats. Okay, and then that particular error goes away. Okay. Okay, let's pop back up. Okay, good. Now, how does one, so I'm just going to show you the 3 functions that we used in my quote-unquote heartbleed chop, right? So unsafe take, pack, and unpack. So unsafe take is really nice. Unsafe take just takes a nat, and it takes a byte string whose length must be greater than the nat, okay? And it gives you back a new byte string whose length is n. And its implementation is super fast. This is it. Okay, you just given an n, given a byte string ps x with some length l, you just throw away the l, and you replace l with n. Okay, that's it. But of course, if you didn't have the signature, then it would be unsafe. You would give me some random n, then this would be unsafe because it will not work out. Right? But here it all works out. The byte string invariants all hold. Life is good. Okay, so unsafe take really, really fast. Next, there was pack and unpack. So let me just show you what pack looks like. Okay, so pack has a signature that looks like this. You give me a string s, and you get back a byte string whose length is exactly equal to the length of s. Okay, so a string s is a set of characters, is a list of characters, and so the byte string's length is going to be exactly equal to the length of s. And here's what pack looks like. I've really only just changed the formatting. So pack takes a string, it calls create with n, which is why we get this len s, because n is in fact just the length of the input string, str, right? But then the filling function is quite interesting. Okay, so what this filling function does, it's a recursive function. It takes the pointer p and then calls go p on x's. And what that's going to do is it's going to recursively just keep doing these pokes. Okay, so it'll keep poking away inside the buffer that P refers to. And if you think about it, there's actually some pretty heavy machinery going in that infers the type of code, because we're not writing the signature. I wonder what that is. I wonder whether this will work. Ugh, it will, but it's scrolled off at the bottom. So much for that. Let's try and see if it works on the, what was it called again? Back. Here's back. Okay, so this has a somewhat non-trivial, oh, sorry. Whoa, that's a bit scary. A good thing we didn't have to write it down. I don't even want to figure out what it is. Oh, that's unpack. It's the wrong function, for God's sake. No wonder it was so scary. Here we go. So let's see, what is going on here? Well, the high-level bit is something like this. If you squint at this, what it's saying is that go, the loop, takes as input a pointer. Notice, see how we're doing pointer arithmetic over here, right? What it's saying is this fellow go takes as input a pointer, and you always have enough. Wait, there's some. Right. Oh, it's all word eights. That's right. That's why. We've done this trick where it's all 1 byte. That's why it all lines up. The size of the pointer P, the plen of P, is always equal to the string that I'm taking in as input. And this is the invariant that's getting maintained. And how do we know this? Well, at this point, I'm calling P go with P and X's. P has the size length of string, and X's has the same size as length of string, right? At each step, when I make this recursive call, I'm bumping the pointer up by 1, and I'm decrementing the size of the list by 1, right? And so it all lines up, which is why this access is within bounds. So for example, if I was to tweak this and replace that 1 with a 10 or 110, then if there was any justice in this world, I would get an error over there. Okay, so it's all lined up to be quite delicately balanced, right? As you peel elements off the list, you bump up the pointer by 1. And these little off by 1 or off by 110 errors won't show up. Okay, there was a question there. Yes?
Yeah, so this is where the magic happens, right? I mean, I've mystified that example. So somehow you infer this invariant that...
I would need another 60 minutes for that. So, but there is some magic going on. I won't lie to you. But it's not that magical. It's actually quite straightforward. But I would have to take another half an hour to explain
I mean,
it.
verifying the invariant, coming up with it
is difficult.
I mean,
So I can give you a quick, for those, if you follow this is great. Roughly speaking, what's going on is there's an abstract domain that we're creating that are essentially all these predicate fragments of refinements that are floating around. And the synthesis or invariant inference simply gives you the strongest thing that you can infer using those predicate fragments.
So all the predicate fragments, all the predicates and subpredicates, or is it just the predicates you're applying around?
They are all predicates that we are scraping from refinement types like this. So they are, the predicates in the refinement language. So the predicates, actually I have an example of a predicate. Let me show you this example, because you need such an example for unpack, which this will demystify when I show you unpack. Here we go. This is a better example. So let me first, so that was just pack. The flip version is unpack, which I was not going to show you, but which is there in the slide, sort of overflows the contents of this window. Unpack does the reverse. It takes as input a byte string and returns as output a string, right, whose length is equal to the length of the input byte string. And this is where a lot of that magic goes away. Okay, it's not shown in the slides, but it's over here. Unpacked, let me blow up the font. This one actually has an even more complicated invariant, right? So here, let's just go blah blah blah, and there's a whole bunch of stuff going on over here. So here, instead of poking, we're going to do peeking, right? Because I want to just suck out the bytes and turn them into a list. And then I'm just going to return when I hit the end of the buffer. I am just going to return that particular list. Where the hell does it go? Peek P, and then when I hit 0, suck out the value P, take the accumulator ACK, throw E in front of the ACK, and just return the result. Okay, so what's going on, if you can read Haskell faster than I can, you start at the beginning of the buffer, you keep reading E, keep throwing them into the ACK, and then when this count goes down to 0, you know you're at the end of the buffer, and then you just take your ACK and you return, right? So here the invariant is actually somewhat more complicated, and I had to think a little bit about this. But the upshot is it gets nicely summarized into this predicate fragment that I've named unpack, because it gets used over here. And what this predicate is doing is, Lord help me, what it's saying is, roughly speaking, the size, remember this returns as output a list, the size of that output list is 1 plus n is going to be this counter, plus the size of the accumulator. Okay? And this is really just, I mean, these you could alpha, so this is what I mean by a fragment. This is one of those fragments. Right? You could alpha rename this. In fact, you could just replace those v's with underscore, underscore, underscore. Right? Now, this is a kind of weird fragment, and it comes out over here in this corner case. But I'm extending the abstract domain with this fragment because as it happens, you use it in unpack, but the same pattern appears in a bunch of other places in the library. And once you sort of encapsulate this pattern as one of these qualifiers, it gets used elsewhere and saves you from having to write down a whole bunch of types like this. Yeah?
But we can't infer the existence of this thing. You have to annotate this explicitly.
You have to, sorry. If I did not write this, I would get an error. If that's the, so if I deleted that qualifier and I sort of jostled this so it actually triggered the checker, then I would get some kind of error. Why am I not getting the error? Because I haven't actually jostled, because I haven't saved the file, that's why. Please give me an error. I don't get an error. I have no idea why that didn't happen. I know the error is there, please. It is late. Ah, there we go. There's the error. So it says, I can't prove that the length of the output is equal to the length of the output. This fact is, I don't know that. Right? And the reason you can prove this is only because there's this really strong postcondition about Go. And the only way you can even state that postcondition is you need a predicate fragment like that. Okay? So this is one of those very rare cases where we actually had to make up a fact that was outside the sort of general pool of facts that we were talking about, and so we had to write it down. But in the vast majority of cases, it just picks up facts from the specification that you're trying to change. Yeah?
Can you show the error message?
Do you really want to see it? No, I'm kidding, I'm kidding. No, here we go, here we go. The error message is unfortunately not very helpful. What it says, I will read it out to you. It says the inferred type is that the length is greater than equal to 0. Oops. But what is desired is that the length is equal to the length of A, where A was the input. And I have no idea that, why is it equal to the length of A. Right? And the reason it's equal to the length of A is because, I mean, there's this weird arithmetic going on over here, which is captured by that fact out there. Right? So anyway, for my own benefit, I shall pop that back in, and let us go back to the slides. Okay, so that's unpack. And you get the idea, see the source. So I have a little handy comment over there. And now that we've written on the type for pack, unpack, and so on, you sort of repeat for all the 700 other functions that are exposed by byte string. Now you're on sort of safe ground, because now you can write functions like chop and be sure that bad things won't happen. So for example, if I just wrote a random chop like this, string in string, it'll be like, I don't like this. N could be any random number. The byte string that you created has nothing to do with N. It's reds all around. Right? I do not like it. But you can fix it by writing down a signature that says, don't worry, I'm going to give you S, which is a string. The number that I give you will be less than the length of S. No need to freak out. And in that case, the output you will get is in fact a string whose length is equal to N. And then it all works out quite nicely, right? Because that's the property you want to have. This apparently does not work. Why is that not working? 30. I bet I didn't run it properly. What? So this should have gone rejected, but it's not getting rejected. Damned if I know why. Something's not working, life is short. What are you going to do? Oh, I know why, I know why. Because this is why. Because this was, oh, Lord help me. Give me a sec. Let's go back to chop. Because we're using the bogus chop. So now when I do this in my demo, with any luck, oops. Yeah, so that error has gone, and it will be replaced by an error down here because this 30 is out of bounds. Oh, mighty 30. I promise it will show up. Once I say, there you go. Okay, so this 30 is out of bounds because Ranjit has length 6 somewhere, right? This one is fine. Okay, so that's pretty much it as far as memory safety goes. So, I mean, this is roughly how it works. You start at the bottom, you write types, and then you have to dredge those types up the kind of call stack, as it were, all the way to the top, right? And at each step, you use the types from the previous step to make sure you aren't doing something wrong. Okay, so I should just wrap up. Let me, in the interest of, let me just cut right to the chase, which is, what was 12? Was it 10? Give me a second. I will just conclude. Da, 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 da. Laziness, termination, evaluation. Yes, evaluation. That's what it was. Evaluation. Okay, good. There was a whole bunch of stuff. We shall skip. We built this tool. We've thrown it at a bunch of libraries at this point. About 10,000 lines, 56 modules, which is a lot in the real world, but a lot in the research world, I guess. We've checked a whole bunch of different kinds of properties. So memory safety, I gave you a feel for what we did. I say functional correctness with a little star because what does that really mean? It means different things for different libraries. Another thing that I didn't talk about is, as it happens, you need to worry a little bit about termination because laziness has some strange effects in the refinements world, right? It doesn't matter in call by value, but when you're in call by name or call by need, as it happens, you have to worry about termination as well. In all of this, we found that this procedure of this magical procedure where we synthesize invariants is crucial. And let me just give you a very simple example. Actually, I gave you a very simple example at the very beginning. You remember this 001 refinements.hs where I call sum. So over here, just every occurrence of $, there's a whole bunch of inference going on just to figure out what the A's and the B's are. And it would be impossible to use any of these fancy dependent type systems unless you had some reasonable story for figuring out how to instantiate the polymorphic type variables. Okay, so there's a whole bunch of inference that goes on right there, or even the type of fault. Here are some of the libraries, right? XMonad, StackSet, GHC's list, vector algorithms. I guess the two big ones are data text and byte string. There's various other libraries in there. It's about 11,000 lines. I guess the upshot is something like this, right? Where if you look at, this is the size of the code, and this is the amount of stuff, roughly speaking, that you have to write in those curly braces. It's not too bad, I guess, is the upshot, right? I'm one of those data illiterate people, so everything is sort of painted in blue and green just so I can understand. It's roughly 1 in 10 lines, somewhere between 1 and 2 in 10 lines, right? So it's not like you write 100 lines of code and then you have to write 2,000 lines of specification. It's quite modest. 8.5%, I guess, is the average. Oh, the running time, what is this? It's like roughly 1 second per 100 lines, or is that 10 seconds per 100 lines? I can't do the math. I think it's 1 in 10, right? It's about a second per 10 lines, plus or minus. The really interesting thing that I found going through this entire exercise of checking these libraries is that very often, we always say this, right? That types are machine check comments. And you find this. You often have requirements. The folks who wrote text and byte string are really smart people. And so, they can't use Haskell to encode these kinds of weird pointer arithmetic invariants. So they've written them down in very crisp English. So here are some examples. In data map, which is a binary tree, right? It's a binary search tree. It's with various sophisticated ways of balancing and so on and so forth, where we check the binary search ordering invariant and various other things. So here's a comment. Join assumes that all the values in the left subtree L are less than K and all the values in the right subtree are greater than K, and that L and R are valid trees. Right? So this is all in English. But as it happens, you can write this quite cleanly inside of type. Here's K, here's the left subtree. Everybody in the left subtree is less than K, everybody in the right subtree is less than K. And the fact that they are valid trees is, in the binary search tree ordering, is captured by the fact that they're both mapped. Right? So it captures exactly what's in the comment. All those things those gruesome things I showed you in byte string, they're all, like Duncan Poots and one, they know about all this, right? So all of these things are written in English. So the unsafe byte string omits the bounds check, which means there's an obligation to ensure that the bounds are checked in some other way, right? And well, we can just put the bounds check inside the type, right? And then it gets checked all the way around. Here's another one. So that unsafe take has the comment, omits the check on n that there's a, omits the check on n that it's valid. So there's an obligation to provide a proof that n is between 0 and the length of x's. Here you go. It's just captured right inside the type. And that's pretty much it. I think I am done. Conclude. Types are very nice. Lots of properties. Inference is great. take home, I guess types are a nice way to analyze all the fancy features we like in Haskell. Where are we going to go with this? Well, right now we want to make it even faster. I think it's pretty fast. It's not unusable. But really the hard thing over here is error messages, as I think with any type system. This is really the hardest technical problem. And I think what makes this error messages problem even harder is that even though it's a technical problem, it's kind of a squishy problem. It's not like something you can prove a theorem about or run some benchmarks. It's like, what is a good error message? A good one is something that a human can understand, and that's a difficult thing to worry about. Okay, that's pretty much it. You can do this. I should have had a cabal install Liquid Haskell. Apparently it's really easy to install now. My student Eric has made it so you can even run it on Windows. This is a lot harder than that. And with that, thank you very much for your indulgence.
Thank you so much for coming out. That was excellent. That was excellent.
I guess that was a long talk. I'm sorry, I went.